Right, here we are. My name is Mr. Jackson,
And I'm Miss Hughes.
and this is Unit 2, and we're still in our first module on combinatorics. We finished our unit on permutations, and now we're moving along into an area of combinatorics called combinations. Okay, so we're looking now at a whole way of counting where maybe order isn't important anymore, and that's really what this unit is devoted to, is looking at how do you count arrangements of things when really the order doesn't matter.
Yeah. We care what we have, but not what order it's in our hand, say.
Yeah. So what we're going to do, in the same way as last unit, we started by looking at tree diagrams.
And even lists.
And even
just
lists,
making a systematic list.
Systematic list.
Yeah.
We're going to look at another way of organized counting and another tool that will help us to visualize some of the relationships. And this tool really comes in handy all across counting systems where it's important to keep track of things that belong to one group and things that belong to another group. And we're really going to hit on mutually exclusive and then not mutually exclusive things when we start keeping track of Venn diagrams.
And that little area of overlap in the Venn diagram.
Yeah.
And you probably have used Venn diagrams in a lot of your other courses to organize your thinking.
Yes.
When you compare prokaryotic and eukaryotic organisms, you'd use a Venn diagram because they do have similarities and differences. And we're going to look at how we can use Venn diagrams strictly mathematically, so not necessarily concept-driven, but numerically.
And in fact, students are introduced to Venn diagrams in mathematics early.
Yeah.
And so they're probably things that you've seen maybe at the grade 5, 6 level, but now we're going to add some sophistication to that description.
Right.
So we're going to start, I think, with some definitions and some terminology. And so I'll begin by giving you a basic rundown of the basic definitions that we're going to need, and then Ms. Hughes will take over and give you some more in-depth definitions. So when we're talking about sets and counting, a set really is an unordered group of items. So it's basically a group of items that represents data that's just unordered.
Yeah.
And we say that, the set of all prime numbers, between 1 and 10 would be 1, 2, 3, 5, and 7. And sets are always given a capital letter.
Yep.
And the elements of each set, as you can see here, are included in curly brackets. And so here we'd say the set of prime numbers, and we would define that set as 1, 2, 3, 5, and 7 if we were looking at the prime numbers between 1 and 10.
That's right. And notice here that we've put them in a particular order, but those curly brackets are really saying that it doesn't matter what order. You could have 1, 3, 2, 7, 5. It's like a bag of numbers. You don't care what order they're in, just that they're in that bag, as opposed to numbers being laid out in a row.
Yeah.
And so that set is like saying we have these numbers, we have a bunch of numbers, they're in the set of prime numbers. Yeah. So we've written them in an order, but order doesn't matter inside of a set. We
could also say, hey, here's another set, and this would be the set of even numbers between 1 and 10. And that would include 2, 4, 6, 8, and 10. Again, the order wouldn't matter. It's just that the fact that these are the even numbers between 1 and 10, and they fit into this description. Okay? So carrying on then, an element follows directly from what a set is. And an element is an item or a member of a set. So a member, say, of the even numbers between 1 and 10, a member of that set is 6. Okay? And so elements of a set are given a small or a lowercase letter, and we have this kind of scripty, strange-looking E, which is a mathematical symbol for element. So an element X of the set capital X is a correct notation to talk about the element of this particular set.
And we could say 6 is an element of E, and we would write 6E.
Yeah.
Capital E, so that you could see that. Now you've used elements and you've used sets because you've worked with this set of all real numbers. And when you do domain and range, you would say X is an element of the set of all real numbers. And you use those curly brackets as well because, again, order doesn't matter, just that the
Yes.
values are in there. So
Yeah.
you've seen this kind of notation probably in grade 11 when you've done domain and range as well.
Yeah. So let's start by defining then the universal set. And the universal set would be the set of all items involved in a particular situation. So in general, we're going to talk about the context of the problem that we're trying to solve or the context of the situation that we're looking at. And the universal set is the largest set, and it includes all the items that are involved in a particular situation. So we could investigate some phenomenon at KCI. And if we're talking about students that are involved in any particular situation, our universal set would be the set of all students at KCI.
Yeah.
Okay.
And often you can think of your universal set, if we go back a ways, as your population maybe. You know how we have population, sampling, frame, and sample. And we even used a Venn diagram then to show you what that was all about.
Exactly.
Yeah.
Here, in general, the universal set often has the capital letter U. In fact, that's the notation that we're going to use. But notation, of course, changes from course to course. And so you may see professors or other teachers using a capital letter S to represent the universal set. We're going to stick to U in our notation as we go through. Of course, the exact opposite to the universal set, which is the set of all items, would be the empty set or the null set. And that would be a set that has no elements. And so let's say we have a null set, which would be X, and that would have no elements in it. And sometimes you'd see a 0 with a slash through it, so you could say X equals, and then a 0 with a slash through it. The null set becomes important in applications a little bit later on. So perhaps you're talking about a group of students at KCI, and there basically isn't anyone to represent what we're talking about. That would be an empty set.
Yeah, and so
you're, an example would be, the set of KCI students who are above the age of 35.
Yeah, that would be an empty set.
That would be an empty set because there aren't students at our high school at the current time that are older than 35 years old.
That's right. And the null set, too, it is, by definition, because it's the set with nothing in it, then it's the set that gives you the option of taking nothing as well. So if you want to have the option of saying, I don't want any of those options, then that option itself is called the null set, and it represents one choice.
Yeah.
Okay.
So whenever we then want to characterize sets, there's a couple descriptors that we can use. And this small letter n that you've seen before, certainly throughout the permutations unit, is basically the number of elements in a set. And we would use this notation if we want to talk about the number of elements that, say, represent, maybe these two sets up here. So certainly we could say the number of elements in the set E would be 5. Yeah. And it's because there are 1, 2, 3, 4, 5 elements within this set E.
So notice the difference when we're defining a set. We're saying E is the set of all even numbers between 1 and 10, which are 2, 4, 6, 8, and 10. But then over here, we can say a little more information about that set, which is that the number of elements in E is 5. So these are two very different pieces of information about a set.
Yes.
One where you define it and or list what's in there, and then the other one where you just say how many there are in that set.
Okay. So a subset then is a set whose elements are also elements of another larger set. Okay, so say the set of even numbers between 1 and 10 is a subset of an even bigger set, which is, hey, the even numbers between 1 and 100.
Yeah.
Right?
Yeah, so it's a proper subset. Just like how the sample is a subset of your sampling frame.
Yeah,
which is a subset of your population. Yeah.
So here, for example, the set M, which equals to 2, would be a subset of either E or a subset of P, because that would be found in both.
All right, so now let's talk about what do they look like, and what are the different elements, and what does it mean to have an intersection or a union on your Venn diagrams. So when we take a Venn diagram, usually we use circles to represent different sets. And we start out with a rectangular box, and we're going to do anyway, top left corner, we put the capital letter U, and we're saying this rectangular box is the universal set. It's all the things we're talking about. Within that universal set are subsets, and those subsets are represented by circles. If there's any area of overlap, the circles you'll be able to see that area of overlap. If not, the circles will be distinct. So then, you'd be able to tell whether or not you've got elements that are in both. So this diagram that uses circles to represent the relationship between sets, this is the Venn diagram. Now, what the two sets have in common, if we were to use E and P from above, so the even numbers and the prime numbers, any numbers that are both even and prime would exist in that area of overlap between those two circles.
And so graphically that completely makes sense, that you would have an overlap, and that represents the elements also that overlap.
All right, so now let's look at a union. And what does it mean to have the union of two sets? So if we take our two circles, we take our two sets, union is saying, well, what are the elements that are in E or P, but not both, like no double counting.
Yeah, no double counting.
No double counting. I'm interested in E and P. I want to know what are the elements that are in E or in P, but no double counting. So essentially, we're taking all the elements that were in E, all the elements that were in P, and then we have to remove out the one we double counted so that everything is just being counted once. So we can say in words E or P. We can also write E union P. So that U is representing the word union there. So the union of set E and set P is 1, 2, 3, 4, 5, 6, 7, 8, and 10. Notice we didn't write 2 twice, even though it does appear in both. Of course, 9 isn't in there anywhere. So the union of E and P is the elements that are in E or P without any double counting. And we could count that number now because we haven't counted the 2 twice.
Now, for notation's sake, this union, this little symbol here that we're using for union, is really like a horseshoe. It's just there's no tail on the U. It's basically just like a horseshoe magnet. It's basically like a U that's upside right. And you'll see that that's a little bit different when we talk about the intersection.
All right, so the intersection is represents the elements that are in both E and P. So these are the ones that can be seen in set E and in set P, but not just in one or just in the other. So if we were to shade that in, then the only area we'd be shading is the overlap. So we're only interested in where is the overlap? Where do we find an element that's in both E and P? And we write that as the upside down of the union. So E intersect P is the number 2. Okay, so the elements where E and P intersect, that's just going to be one element for us in this case, which is the number 2. You'll see we've underlined the word and the word or. And again, in this unit, and or are important, just like they were with permutations, because they mean something different. And means the intersection, and or means the union. Okay? And we can replace that horseshoe with the word or, and we can replace that upside down horseshoe with the word and.
Okay, so let's take a look at a principle that we're going to use. It's the principle of inclusion and exclusion for 2 sets.
There's the number 4 in case you're wondering.
Yeah, so that little number 4 will become important in a minute. But we're going to take a look at this principle by way of example. Okay, so let's say this semester, there are, of the 29 students that are taking drama, 18 have signed up for a play that will tour several high schools. 12 have volunteered to help out in the drama festival, maybe the Sears Drama Festival. 5 students have agreed to do both. So let's illustrate this solution with a Venn diagram. So let's illustrate this whole situation using a Venn diagram. So of course, because we're talking about 2 groups, right? So we're talking about 2 sets. Students that have signed up for a play and students that are helping out with the Sears Drama Festival, we're going to have 2 circles. And so let's say, first, for posterity, we're going to label what our universal set is. And that's usually the first step that we take. The universal set, in this case, is the set of all students that are in drama.
And we know there's 29 of those.
We know that there's 29. Here's our 2 circles. And we should actually, at this point, label our circles as A, the set of students who are helping out in the play, which is represented by this circle over here on the left, and B, which is the students that are helping out in the festival, which is over here on the right. And so we'll label this circle A and this circle B. And so What we will say now is, okay, well, let's look at the numbers that we have.
Yeah.
The number of students in the universal set is 29, because there's 29 students taking drama.
Yeah.
The number of students that are helping out with the play is 18. The number of students that are helping out with the festival is 12. And the number of students that are doing A and B, which is both, is 5.
Yeah. So A intersect B is 5.
Exactly.
Yeah. Yeah.
So, at this point, we want to populate our Venn diagram with appropriate numbers. And we know the intersection right away is 5 students. And so if there's 5 students doing both, there are 5 students in the intersection between these two sets. And that's where we always want to start with Venn diagrams.
Yeah.
We always want to start with the center, if possible.
Yeah.
From the center, then we build outwards.
Yeah.
And so if there are 5 students that are doing both, let's talk about then A, which is the number of students that are in the play.
So we know there are 18 students in the play altogether.
So this entire circle
is 18.
Is 18.
But we know that 5 of them are actually doing both. So picture that these are giant hula hoops, and you've asked the 5 kids who are doing both to stand in this area of overlap. But there are only 18 students overall, so you don't want 18 more students standing on the other side.
No.
You want there to be 18 students in that hula hoop altogether.
Yes.
And so you're going to take 18 minus 5, and that's the remainder of the students that are in that set.
Yeah.
That make up all the kids that are in the play.
Yeah.
Okay,
so if we look at this, we see, okay, first of all, do we have 5 kids that are doing both? Yes.
Yes.
Do we have 18 kids that are helping out with the play?
Yes.
Because 13 plus 5.
Yeah.
So we've covered this circle and we've covered this set. Had we placed an 18 here, we would be, of course, incorrect, because then we would be saying that we'd have 18 plus 5 students in this circle helping out with the play, and that's not what we have.
No.
We have 18 students in total helping out with the play. On the other side, let's look at students that are helping out with the festival.
All right.
The total, this number of students that are helping out with the festival are 12.
Yeah.
Right? And again, going back to this hula hoop analogy, we've already got 5 of those 12 students that are standing in the hula hoop.
In the right hula hoop, yep.
Okay.
That's right.
So then that means that out here, the students that are in the class and they're helping out with the festival, but they aren't helping out with the play, is 7.
Yeah.
Okay. So when we put all of this together, we say, okay, well, how many students do we have represented here? Well, we've got 13.
Yep.
Plus we've got 5.
Yep.
Plus we've got 7.
Yep. We've got
And so
25.
there's 25 students standing in the hula hoops.
In the hula hoops.
Well, there's 29 students in drama.
In drama. So there must be some people standing outside the hula hoops that are still in drama.
Yeah.
And those are the 4 leftover kids who are part of the universal set, but not part of sets A or B.
Exactly. And who knows what they're doing? There's no information to describe that.
Yeah.
We still count for them because we know how many are in the universal set here. We still have to count for them. And so we just place that number outside of the circles, but within the universal set.
Yeah. They're in drama, but they're not in those other 2 sets.
All right, so now we get to ask the questions. How many students are involved in at least one of the productions?
Yeah. So one or the other or both.
Yeah.
Right?
So what does this mean? This is basically asking for the union of the 2 sets.
Yeah.
How many students are involved in at least one of the productions? Yeah. One or the other or both.
But
no double counting.
Yeah.
So here we'd have n, the number, in A or B, which is 13 plus 5 plus 7. And that gives us 25 students.
Yep.
Another question, how many students are involved in neither production? And this is what we alluded to, and we said, oh, well, if there's 29 students in drama, and there's 25 that are helping out in one of the productions, or sorry, in at least one of the productions, then 29 minus 25 is 4, and there's those 4 students, and they're not helping out in neither of the productions.
That's right.
So our notation for this is the number of students not in A nor in B, and that's what we would say. And that's basically a very simple Venn diagram problem.
You start with the center, start with the area of overlap, and then you build outwards. Now, we've shown you how to do it on a Venn diagram, and then using logic to add up without double counting, and to figure out what all your values are. But you don't always have to draw a Venn diagram to be able to solve problems involving Venn diagrams. And this is where we're going to take it up a notch from grade 5 or 6.
Yeah.
And we're going to show you the principle of inclusion and exclusion for two sets as a set of formulas here that you can look at.
The formulas, again, are more versatile than the Venn diagrams. Because very often with Venn diagrams, you're not given enough information to completely solve.
Right.
So you need to go to the formulas. And we will see examples of that throughout this unit, is that, okay, well, we don't have enough information yet to solve for the Venn diagram. So we'll go to the equations, or sorry, to the formulas.
We can rearrange to
isolate
a different variable.
Yes.
Yep. So if we want to know the number that are in A or B, okay, so we're looking for the union.
Which is also expressed over here.
Over here, that horseshoe U. Then we just take the number in A, we add it to the number in B, and then we subtract out what we double counted. We subtract out one time that overlap.
Yeah.
Because when you take two circles and overlap them, there is that doubled up area in the middle.
Mm-hmm.
And it's as though we're accounting for that by taking that little extra piece and subtracting it out so we don't count it twice. Okay, so and on the right-hand side, you can see that the number in the union of A and B is the number in A plus number in B minus the number in the intersection of A and B.
Exactly.
Okay.
So let's take a look at how this might work.
Yep.
Again, very simple for two sets.
Yep.
So there's 8 students on a curling team. There's 12 students on the badminton team. There's 3 students on both. How many students are on the two teams combined?
All right. Now, we haven't exactly been given a universal set. So we can put the U in the corner and we can draw a rectangle and we can put in our 2 circles, one circle for the curling team and one circle for the badminton team. But we don't know how many are in the universal set, if it's like all the teams or what it is. So we're not going to define the universal set as being anything in particular. Mm-hmm. But we will put the U there because we do know that these sets are part of something larger probably. Yep. Okay.
You could say this set of all students playing a winter sport, but again, we'd need more information in order to define this, and so we're just not going to define it.
No.
There is a universal set there,
we just don't
and
know
we're
how
going to
many
be happy with that.
Yeah.
So here, let's define what we do have.
Yeah. So we've got the set A will be the people on the curling team, and we know the number in A is equal to 8. Set B will be the badminton team, and we know the number in B is equal to 12. And we've also been given the fact that the number in both A and B, or the number in A intersect B, is 3. So we know that area of overlap. And again, just like we recommended before, you start with the area of overlap, you start with the innermost or most overlapped area, you place your number there, and then you build outwards from there.
Yes. Okay. So let's do that. Let's place our numbers. We're going to start with our with basically, if we were going to populate the Venn diagram right away, we could do that at this point. But
actually, you know what? Let's use the formula first, and then we'll use the Venn diagram, and then we'll show how you get the same result both ways.
Yeah, because what we're looking for is how many students are on the two teams combined.
So we're
looking for the union.
Yeah.
Okay, so we know the number of students that are in A, we know the number of students that are in B, and we know the number of students that are on both. So we can put this together and we can say 8 students on the curling team plus the 12 students on the badminton team minus the 3 students that are in both, because we want to avoid double counting, because there's double counting going on here when we just add these two numbers up. And what we get is we get 17.
Yep.
Okay? And so this is the answer to the question. How many students are there? There are 17 students on the two teams combined.
Yep.
Now, we can also display this in a Venn diagram.
Yep, and we can solve it using a Venn diagram, or we can solve it using the principle of inclusion and exclusion.
Yes.
So we just solved it using the principle of inclusion and exclusion. Now let's look at it by solving it visually on a Venn diagram.
So here we have our 3 students on both, and they're in the middle.
Yeah.
We know that, again, we've got 8 students on the curling team. So imagine this is a really big hula hoop. We've already placed 3 of our 8. So there's a number of students that are on the curling team and they're not on the badminton team, and that would be 8 minus 3, which is 5.
Yeah.
Okay. Over here in the badminton team, there are 12 students total in this big circle. We've already placed 3 of them because those are the ones that are on both. So 12 minus 3 is, of course, 9. And the union of these two sets graphically is the number of students in this section plus the number of students in this section, plus the number of students in this section, and when we add these up, we of course get 17. So basically, through two different methods, one using a Venn diagram and one using the formula, we see that there are 17 students on the two teams.
Exactly.
All right, let's move one step further.
All right.
Let's take a look at the principle of inclusion and exclusion for 3 sets.
Now we can extrapolate this, and mathematicians do this, for 4 sets, 5 sets, 6 sets, more sets.
Yeah.
And we're going to do 2 and 3, but you'll start to see the pattern.
Yes.
And how you can build this in the Venn diagram, and then also how the equations work. Before we introduce the formula for the principle of inclusion and exclusion for 3 sets, we're going to do the same thing we did with 2 sets, which is show you how it works in the Venn diagram first.
Yeah.
And then show you how that translates into a formula that you can use. Okay, so let's say we got a translation service. They have 40 employees. Okay, so they've given us the universal set, of whom 27 speak French, 11 speak Spanish, 7 speak Hindi. Of the Spanish-speaking employees, 5 of them speak Hindi and 6 of them speak French. 3 of the French-speaking employees also speak Hindi, and 2 employees out of these 40 speak all 3 languages. Okay, so this, when you just read this, it's extremely confusing.
Lots of information overload.
Yeah.
And that's what these problems with 3 sets are going to be. And you can just imagine problems with 6 sets and 7 sets. It's overload of information, complete overload of information. So what we need to do, and what I recommend, what Ms. Hughes recommends throughout this whole entire process, is to at the very beginning list what you have and go through very carefully and say, all right, this is what we know.
That's what we're going to do.
So here it is. The universal set is all employees at this company. We know that there are 40 of them. Okay. There are 27 of these employees who speak French.
So the next thing we do is define F as a set of French speaking and the number in F as 27. See, we're just going systematically here.
Then we come to Spanish-speaking employees. There are 11 of them, and so we define this set as S. We define the set of Hindi-speaking employees as H, and we note that there are 7 of them. Once we've established this, now we can look at the intersection of these 2 sets. The problem tells us that of the Spanish-speaking employees, 5 speak Hindi. So that means that there are 5 individuals who speak Spanish and Hindi. It also says that of the Spanish-speaking employees, there are 6 that also speak French. So the number of employees speaking Spanish and French is 6. 3 of the French-speaking employees also speak Hindi. So we've also been given the number of French and Hindi speakers. And lastly, we have the number that speak all 3 languages, which is 2.
So that's a triple intersection.
Yeah.
We've got some double intersections, we've got a triple intersection, and then we've got these singles.
Okay, so let's draw our circles. Here's the universal set. It's inside a box, and there's our 3 circles. Again, the upper left represents the French-speaking employees, the upper right indicates the Spanish-speaking employees, and the lower circle, the Hindi-speaking employees.
Yep.
Principle is still the same. Start in the center
Yep.
and work your way out.
Yep.
So let's place these guys down here, the triple language speakers, into our center.
Our triple intersection.
Okay?
Yep.
Because this represents the number of employees that have all 3 language abilities.
Yep. They're standing in the French hula hoop, they're standing in the Spanish hula hoop, and they're standing in the Hindi hula hoop.
Okay.
Yep.
So here we have the number of Spanish and the number of Hindi speakers. And so really that represents the overlap between the Spanish circle and the Hindi circle, which is right here. Now again, we've already placed 2 of these 5 people. So we shan't write 5 in this circle because that would give us 7 in here.
Yeah.
What we need to do is we say, okay, well there's 5 people, we've already placed 2 of them, so we need a 3 here.
Yeah.
Okay?
Exactly.
We're going to go to Spanish and French speakers.
Yep.
So in this intersection right here,
where the Spanish and the French overlap,
okay,
we've already placed 2.
There are 6 in total.
And there are 6 in total.
So
we
need
just need 4 more that are still speaking Spanish and French, but not also speaking Hindi. Yeah.
And last but not least, the French and the Hindi speakers, which are right here. There are 3 of those. Again, we've already placed 2, so we put a 1 down here to represent 3. So again, good idea to think about your hula hoop questions. Huge hula hoops laid out on the ground. Those 2 people have gone to stand in the middle, and now we've built our way out, and now we're going to continue building outwards. And we're going to start then with the French-speaking employees. There's 27 of them. Okay? How many have we placed in the French hula hoop?
Now we've already placed the 4, the 2, and the 1. So we already have 7 in there who speak French, as well as some other languages. But if we need there to be 27 in there altogether, then we need 20 who just speak French exclusively. Okay, so we just do 27 minus 1, minus 2, minus 4. And that gives us the rest.
And that gives us the rest. Same thing for the Spanish-speaking employees. There are 11 of them that represent this circle here. Now we've already placed 9. Right? So there's 9 people that are already in this circle. So we only need 2 more out here. And last but not least, the Hindi-speaking people. We've placed 3 plus 2 plus 1 is 6. There's only 7 of them, and so we place 1 out here.
That's right.
Okay? Are we done?
Well, we may want to figure out how many employees are maybe speaking something completely different than those 3. But we're going to have to either add up all the values that we see or use a formula, and then what we can do is we can place a number inside the rectangle, but still outside of those 3 sets.
So let's take a look then. This is almost complete. We're not quite there yet, but this is almost complete. So let's take a look at a couple questions. How many employees speak French or Spanish or Hindi? So what this is asking is, of the translation service, what is the union of these 3 sets? And so here it is. The number of people in the union of French and Spanish and Hindi is 27, which was the number of French speakers, and 11, and 7. And then what we do is we subtract off here, double counting, the 5, the 6, and the 3, and then we add in the 2.
Because we've removed it 3 times, and it was only there 3 times, so we have to add it back in so that it appears once.
Okay. The other way that we can look at this is, okay, we'll just count up all the numbers.
Just go back to the Venn diagram and add the 20 plus the 4 plus the 2 plus the 1, and just go through.
So just count up all the things that are in that Venn diagram right now. What you get is 33. And so basically that's how many people speak French or Spanish or Hindi.
Exactly.
How many employees speak none of the languages? Well, here what we do is we say, okay, well, there's 40 people
in the universal set.
In the universal set. And because there's 40 people in the universal set, and we figured out how many speak French or Spanish or Hindi, how many people speak none? It's the difference between those 2. And so the way we represent that is we can actually go back and we can say, okay, well, here it is, and down here then we need an extra 7. Because this then, if we add up all of these numbers in the union, plus the number that represent the remaining employees, we have, of course, our total of 40. So when we come to then the formula for the principle of inclusion and exclusion for 3 sets, we see a very large formula. There's no need to be worried about this because it's very, very simple to follow along. We have basically the union. What's in all 3 of the sets? So the number of elements in A or B or C,
without double counting,
without
omitting anybody,
is equal to the number that are in A plus the number that are in B plus the number that are in C. Now we need to subtract off the number that are in A and B, the number that are in A and C, and the number that are in B and C. And the reason that we do this is because we want to avoid double counting. But when we subtract off these things, we actually subtract off a little bit too much. So those 3 people that are right in the middle, we add them back on. And that's the way the formula works. Again, we're going to look at an example of this in just a minute, and kind of how this works in a problem. using the principle of inclusion and exclusion. But this does look daunting, and it's something that you'll need to have a little bit of practice with. But it really follows very straightforward from each problem that you're given.
Yeah. And, you know, an easy way to remember this, too, this is the same as the principle of inclusion and exclusion for two sets, because what we're doing is we're adding up the singles, right? The number in A, the number in B, the number in C. Then we're subtracting the doubles or the intersections, right? It's just that for this one, when we subtract out the intersections, we subtract out that middle bit that's been triplicated 3 times. So now there's nothing in there, and we have to add it back in. If we were to do this for 4 sets or 5 sets, it would be the same thing. Add the singles, subtract the doubles, add the triples. We would add the singles, subtract the doubles, add the triples, or subtract the quadruples. Like, it just keeps going and going, right? So this principle is the same idea as the one for 2 sets. It's just that the last step after we've subtracted the double intersections is to add back in the triple.
You need to add that back in. Okay, so let's take a look.
Yep.
All 24 condominium buildings in a retirement community have at least one of the following amenities.
All right.
Okay.
Yeah.
So 12 of them have a swimming pool. 12 of them have a tennis court. And 15 have playing card rooms.
All right.
Okay.
Yep.
4 buildings have a pool and a tennis court. 5 have a pool and a card room. 3 very lucky condominium buildings have all 3 of these amenities.
Yeah.
How many at this point, how many of these have only a tennis court and a card room?
So this question is different because they haven't given us everything and then asked us for the union.
Yeah.
Instead, they're saying, well, these 24 buildings have at least one of the following amenities. And whenever you say how many have at least one, you're saying this is the union.
Yes.
Right? So we've actually been given the union as 24, but now what we're missing is that overlap between tennis courts and card rooms. And in fact, one more little piece of information is how many have only a tennis court and a card room, but not a swimming pool.
Yeah.
And so this is where you actually, you can't build the Venn diagram.
Yeah, you can't build it right away from the problem.
That's right.
Because you're going to run into you're going to be stumped.
You're missing that double intersection that you need in order to be able to keep expanding outwards. And so at this point, we have to use the formula, substitute in what we know, and then rearrange to isolate a value that we don't know.
All right, so let's take a look at what we have. The universal set is basically all 24 buildings in the retirement community.
And so is the union.
Yeah. That's the universal set, and that happens to be the union. Yeah. Okay, so going forward then, we're going to talk about the letter P is the set of buildings that have a pool. The set of T is the set of buildings that have a tennis court, and the set C are the buildings that have a card room.
Yeah.
Okay, so here we have the union is equal to the number of buildings that have a pool plus the number of buildings that have a tennis court plus the number of buildings that have a card room minus the number that have a pool and a tennis court minus the number that have a tennis court and a card room minus the number that have a card room and a pool plus those 3 special condos that have all 3.
Yep.
What we notice right away is, oh, we're looking for the ones that have a tennis court and a card room. So our solution is linked to this unknown variable.
Yep.
It won't be this unknown variable exactly, but it's linked to it.
Yep.
So what we need to say is we need to say, okay, let X represent the number of elements, the number of condo buildings that have a tennis court and a card room.
Yep.
And so what we can do is we can now substitute our numbers. We know that there's 24 buildings in the union. We know that 12 of them have a pool, 12 of them have a tennis court, and 15 of them have a card room. We know that 4 have a pool and a tennis court. We do not know how many have a tennis court and a card room, but we do know that there are 5 that have a pool and a card room.
Yep.
We know that there are 3 that have all 3. So from this equation, it now becomes possible to solve for the number of buildings that have a tennis court and a card room.
And a card room, yeah.
And so what we get is 9. when we do this mathematically,
Yeah.
and we bring this over to the other side, we get that x is equal to 9.
Now at this point,
Yeah.
you could take that information and now build your Venn diagram. That was the piece that we were missing. And then you could use that Venn diagram to visually answer the second part of this question.
Yes.
Right? Or you can use your logic. When you picture that intersection or overlap between the tennis court and the card room, there's also that triple that's in there with the tennis court, the card room, and the pool. So if we know there are 9 that have a tennis court and a card room, some of those are also the lucky 3 condominiums that also have the swimming pool. So if we want the number that are only in sets T and C and exclude P, then we're going to take that double intersection and subtract out the triple intersection.
And so there it is.
9 minus 3 is 6.
So 9 minus 3, there are 6 buildings that only have a tennis court
and a card room, no swimming pool.
So that's your crash course on Venn diagrams.